Good morning. I'm Dr. Janardhana rao. We are discussing about operating system. We have covered different topics and concepts. Today, we'll discuss about dynamic memory allocation and deadlock concepts. Previously, we discussed about swap space management. Modern systems typically swap out pages as needed rather than swapping out entire process. Hence, the swapping system is part of the virtual memory management system. Managing swap space is obviously an important task of our modern OSs. So, swap space use. So, whenever in the concept of virtual memory, in the paging concept we have seen swap in, swap out. So, we'll create space for the newly incoming pages in the main memory. So that time we will go for the swap in. So the amount of swap space needed by an OS varies greatly according to the how it is used. The some systems require an amount equal to the physical RAM. Some want a multiple of that RAM size. Some want a amount equal to the amount by which the virtual memory exceeds physical RAM, and some systems are little so none at all. So some systems support multiple swap spaces on separate disks in the order to speed up the virtual memory system. So swap space allocation. Swap space can be physically located in one of the two locations. So as a large file which is part of the regular file system, this is easy to implement but inefficient. Caching the block location helps in finding the physical blocks, but this is not a complex fix. As a raw partition possibility and a separate or a little used disk, OS more control over swap space management, which is usually faster and more efficient. The downside of the keeping swap space on a raw partition is that it can only be grown by partitioning the hard drive. So that is swap in swap space. So this is like this. Historically, voices swapped out entire processes as needed. Modern systems swap out only individual pages and only as needed. So we have seen the paging concepts in the virtual memory management. In the mapping system shown below for Linux system, a map of swap space is kept in memory where each entry corresponds to a 4 kilobyte block in the swap space. Zeros indicate spree slots and non-zeros refer to how many processes have swap mapping to the particular block. So here, whenever we required or deleting a file, so we'll clear that space. So that is we're clearing means deleting means we're swapping out. That will become a hole left in the memory. So if you look at this in dynamic memory allocation, so what is dynamic memory allocation? Dynamic memory allocation is when an executing program requests that the operating system give it a block of main memory. The program then uses this memory for some purpose. Usually, the purpose is to add a node to data structure. In object-oriented languages, dynamic memory allocation is used to get the memory for a new object. The memory comes from above the static part of the data segment. Programs may request memory and may also return previously dynamically allocated memory. So memory may be returned whenever it is no longer needed. Memory can be returned in any order without any relation to the order which it was allocated. The heap may develop holes where previously allocated memory has been returned between blocks of memory still in use. So we look at this one. This is our RAM or hard disk, anything. So when you are executing program, some of the space used as a heap. In the heap, we store some methods. So when method is executed, so when it is for executing, the program will request the OS to allot the memory. So the memory will be allotted to the methods by the OS for the particular method, that process. So whenever the method is completed, then it will be getting this one. So this is nothing but a free space or hole. So memory may be returned whenever it is no longer needed. Memory can be returned in any order without any relation to the order in which it was allocated. The heap may develop holes where previously allocated memory has been returned between blocks of memory is still in use. Memory is still used. So that's mean the function, that method, what for method we have allotted some memory, that memory method is not executing over, then it will return it handover to the OS. So dynamic memory allocation, a new dynamic memory request for memory might return a range of addresses out of one of the holes. Holes means that is empty area, empty space. So already allotted to some process. Once that process is executed, then it will return that memory to the OS. Like example, heap. So we'll see heap. This is after executing the method, it will return that memory, whatever we allotted, to the OS. OS will allocate that memory to some other process. So, but it may not use of all the whole. So, further dynamic requests might be satisfied out of the holes. It may be not used for all the whole. So, further dynamic requests might be satisfied out of the original hole. If too many small holes develop, memory is wasted because the total memory used by the holes may be large. So, as it means, suppose this is our memory. So we have given space for the different methods, different programs, a different process. Once they executed and they return back. This is one, hole two, hole three, like this. So when they return, in between, suppose three is handing over. So now three is one hole. Like this, there will be different holes will be formed. So if it is kept like this, whatever maybe size may be, but they'll be wasted. So that is not, that is small holes will be in between the memory allocations. That is vacant. So that vacant place is called hole. If too many small holes develop, memory is wasted because the total memory used by the holes may be large, but the holes cannot be used to satisfy the dynamic reverse because the hole size may be small. The situation is called memory fragmentation. Wastage of memory is called memory fragmentation. Wastage of memory. So we cannot use that memory for any purpose because that is used by somebody, but handed over the memory to the OS. So keeping track of allocated and deallocated memory is complicated. A modern operating system does all this because the modern operating system will combine these holes. This is one hole, this is one hole, one, like these holes are there. This is we cannot because since it is space is less, we cannot allow these holes to some other process dynamically because the may be less. Because of that reason, this is wastage of memory. So if you combine all these holes dynamically, it means you can move rest of the memory some one side and holes one side. Then you will get big data, big space. So we can allot. So a library function is linked to the user program and executes in user space, while system call is not linked to a user program and executes in kernel space. A library function execution time is counted in user level time, while a system call execution time is counted as part of the system time. So library functions can be debugged easily using a debugger, while system calls cannot be debugged at they are executed at kernel level because whatever system calls available at the kernel, that is not the users mode. They are kernel mode. We cannot touch this system calls. So some of the library function can be checked, but kernel functions cannot be checked. So the next in this session we are discussing about some of the concepts. So, for the purpose of deadlock discussion, we discuss about deadlock. So, for the purpose of deadlock discussion, a system call can be modeled as a collection of limited resources which can be partitioned into different categories to be allocated to a number of processes having different needs. Resource categories may include memory, printer, CPU, open files, tape drivers, CD-ROMs, etc. So, by definition, all the resources within a category are equivalent, and the request of the category can be equally satisfied by any of the resource in the category. So, when the program is being executed, when the processes are requesting for the resources, maybe IO, maybe CPU, maybe tape, maybe any files. So, once they're requesting, the OS must be in a position to allocate these resources to the process for the smooth functioning of the execution. So that's system model. So by definition, all the resources within a category are equivalent, and a request of this category can be equally satisfied by one of the resources in that category. So we just will go forward to the detection, the deadlock and all. So every process needs some resources to complete the execution. However, the resource is granted in a sequential order. So we have seen that. So this is a program we write in the C or Java. So this is a program. This we give the name for this program. When it comes for the execution by CPU, so the OS will monitor and it will send one by one. If it is executing, this instruction is executing, if it requires some it requires some IO input. So OS has to supply to this instruction for execution in the CPU. So that's what resource allocation. So resources available, but when any process is requesting for um, resources, so it must be in a position to allocate the resources to the process for execution. The process requests for some resource. OS grant the resource if it is available, otherwise let the process waits. The process uses it and release on the completion. Because as we discussed, the process is nothing but program under execution is called process. So the program means whatever you program, we write in the Java or C or Python. So there may be 100 lines or 1000 lines, but each line should be will be executed by the CPU. So once is coming for execution, the process is requesting for the CPU. So CPU is free means the OS must be allotted that resource to the process or instruction to execute. Instruction to execution is called process. So a deadlock is a situation where each of the computer processes waits for a resource which is being assigned to some other process. In this situation, none of the process gets executed since the resource it needs it held by some other process which is also waiting for some other resource to be released. So suppose this is your CPU and these are the program, and we are executing the program one by one, instruction 1, 2, 3, 4, 5 like this. So like this, if already number 2 is holding some variable, it is not releasing. Now 1 has come for the execution. So if one wants some that resource from the 2, if 2 is not releasing, that 1 cannot be executed, never ever. So that's is holding. So deadlock is a situation where each of the computer process waits for a resource which is being assigned to some other process. In this situation, none of the process gets executed since the resource is its needs. It held by some other process which is also waiting for some other resource to be released. So that's the concept here. So here the process will be executing. For execution, it requires some resources. Resources may be process, or file, or the variables, or anything. So unless they get it, it can't execute this process or terminate from the CPU. So on that condition, the process will be requesting OS to release that process, release that resource for him. So OS cannot allocate because already is allotted to some other process. So it is keep on waiting. So ever. So that condition is called deadlock condition. The deadlock condition, the system will get hanged up. So every process needs some resource to complete the execution. However, the resource is granted in a sequential order. Example, A want to call B. At the same time, B also want to call A. So that is um, both are on the same track. So if one A wants to call, B also want to call. So they never ends. The problem never solved. That's called deadlock. So this is introduction to deadlock. Every process needs some resources to complete the execution. However, the resource is granted in a sequential order. Suppose R1, R2 is a resources. P1, P2 is processes. So P1 is accessing R1, but P1 is requesting to R2. P1, P2, R1, R2. Already P1 is having R1 and it wants requesting R2. At the same time, P2 is holding R2, it is requesting for R1. So, for execution of P1, it requires R1 plus R2, both to execution. At the same time, for P2 execution, it requires R1, R2. So, P1 is holding R1 and requesting for R2, whereas R2 is held with the P2. So, P1 will not release R1, P2 will not release R2. So, then the system will be in deadlock condition. So, this is what is meant by deadlock. So, system will not get executed. The program will not be executed forever. That is called deadlock. So in this manner, in this scenario, so let us assume there are three processes P1, P2, P3, and there are three different resources R1, R2, R3. R1 is assigned to P1, and R2 is assigned to P2, and R3 is assigned to P3. So P1, P2, P3, R1, R2, R3. This is assigned to P2. This is assigned to P2. Already assigned. So now, after some time, P1 demands R1 for R1, which is being used by P2. So like this, it demands for this one, and he demands for this one, and he demands for this one. So like it's interlocked. So no one is once it is allotted, they won't release unless they execute, because for execution it requires another resource. So that resource is held with somebody else. So that's the main case. So ultimately P3 also demands for R1, which is being used by P1. Therefore P3 also stops its execution. That is a problem. They want all three resources for execution. So if nobody releases unless it executes, then system will not execute it completely. So this is a deadlock. In this scenario, a cycle being formed along with the three processes. None of the processes is progressing and they are all waiting. The computer becomes unresponsive since all processes got blocked. We look at one. This is allotted to P1. This is allotted to R2 is allotted to P2. R3 is allotted to R3. But P1 is requesting for R2 and P2 is requesting for R3 and P3 is requesting for R1. So nobody is releasing. P1 is not releasing R1, P2 is not releasing R2, P3 is not releasing R3, but they are requesting other resources because they want for execution they require another resource also. That resources is being held with somebody else. So that is a problem here. So that is it became a cycle. In this case, system will not execute. So this condition is called system stuck or deadlock. So we'll see what is starvation and what is deadlock. Deadlock is a situation where no process got blocked and no process proceeds. Starvation is a situation where the low priority process got blocked and the high priority process proceeds. Deadlock is an infinite waiting. Starvation is long waiting but no infinite. So every deadlock is always a starvation. Every starvation is need not to be deadlock. The requested resource is blocked by the other process in the deadlock. The requested resources continuously be used by the high priority process. Starvation means keep on waiting. It sometimes get cleared by some because one process requires some resources that low priority process, but that whatever low process required the resource that is held with the high priority resource. So unless the high priority process completes the execution, it won't release. So after releasing only, the resource will be used by the low priority resource. So the deadlock happens when mutual exclusion, hold and wait, no preemption, and circular wait occurs simultaneously. It occurs that starvation occurs due to the uncontrolled priority and resource management. We'll see deadlock is a situation where a set of processes are blocked because each process is holding a resource and waiting for another resource acquired by other process. Because we have seen the previous diagram, P1 is one process, P2 is one other process. P1 is holding this one resource R1 and it wants R2, which is held by P2. Same way, P2 is holding R2 and it is requesting for R1 because P1 is not releasing, P1 is not releasing R1 and P2 is not releasing R2. So, in that case, both are stuck up. So, consider an example when two trains are coming towards each other on the same track and there is only one track, none of the trains can move and once they are in front of each other. So, the similar situation occurs in operating system when are two or more processes that hold some resource and wait for resource held by the others. So, for example, in the below diagram, we'll see process 1 is holding resource 1 and waiting for resource 2, which is acquired by the process 2, and process 2 is waiting for resource 1 and requesting for another, which is held by process 2. So this is process 1, the process 2, and process is requesting for, it is holding, process 2 is holding resource 2 and requesting for the resource 1, but it is held by process 1 and requesting for the R2. So this is how the struck off will take place. So this is called deadlock condition. So deadlock can arise if the following four conditions hold simultaneously. So this is mutual exclusion, hold and wait, no preemption, and circular wait. We will discuss these concepts in the next class.
Like, share and subscribe. Hit the bell icon for more updates.